Hello, everybody. I am a horrible liar because I told you guys that there are only two parts to this whole improper integral thing, but it turns out that there are three parts. Well, technically, this last part is really kind of like a small little minor snippet, but it's still something in there. So how about this? Let's just go ahead and compromise and say that this is not part 3, but part 2.1, just to make it a little bit better. So this part of the calculus that we're looking at is something called the comparison theorem. So we are still looking at improper integrals, but this time we're going to use something. It's kind of like a neat little trick to show you how to solve for if something is convergent or divergent without having to do a lot of work. So that's why I felt it was necessary. So here we go. In the illustration on the right-hand side, you can see over here, what I have are two equations or two graphs. And it's always going to be a case where one is the upper function and the other is going to be lower function. And they're both going to be always positive just to make things easier. So the setup is that the conditions are that let f of x be greater than or equal to g of x is greater than or equal to 0 for all x that is going to go from a to, let's just say, infinity to cover everything. If it's the case where if the upper function is going to be convergent for the area under the curve, then the conclusion about what is underneath, which is g of x for the same boundary, that conclusion is that this is also going to converge. So let me go ahead and sneak that in right there. So this is going to be convergent as well. Okay, and the reason is, well, if you have an area under the curve which is always going to be higher or bigger than the one that's below, and the one that's above is convergent, then therefore the one below it has to be convergent as well. And similarly, if we were to kind of flip that around, let's say this time that if we were to look at the underneath function g of x, let's say that under function is going to be divergent. So from here, this guy right here, there's no finite number that is going to be defined as this. So maybe let's say the area under the curve is like, say, infinity or something like that. So once again, the area under the curve for g of x from a to infinity is divergent. Then the conclusion about any function that is bigger than that under the same boundary must have the same conclusion as well. So that means that this has to be divergent as well then, as a result. Now, all of this so far sounds pretty trivial, but you'll see how this is actually going to be very useful in just a little bit. So here's an example of a problem where I want to solve for if it's going to be convergent or divergent. So I have an improper integral. So first, what I'll do is I'm going to go ahead and think about the following. Okay, this is not something that I can actually integrate. Well, I guess I can, but it might take a little bit of work, and you might not remember what it is. But what I do know is that it does look somewhat familiar in terms of something that I can integrate. And that something is going to be 1 over 1 plus x squared. So if you look at the two functions, 1 over 5 plus x squared, and then 1 over 1 plus x squared, since x is going to be something that is greater than 0 because of my boundary over here, then I can conclude that this is going to be underneath it. So what I'm doing is I'm going to take my improper integral and I'm going to compare it to the integral from 0 to infinity of 1 over 1 plus x squared dx. Okay, so that one, now what I'm going to do is I'm going to go ahead and set up the improper integral, limit as a approaches towards infinity of the integral from 0 to a of 1 over 1 plus x squared dx. Now we could go ahead and take the antiderivative. So limit as a approaches towards infinity of tan inverse, that's what it's equal to, right, of x, and then boundary from 0 to a once again. Then for this part, it's going to be limit as a approaches towards infinity, plug in the boundaries. So tan inverse of a, and then minus the tan inverse of 0. This guy is equal to 0, so that's easy enough. And this guy over here, if you remember from a while back, we were talking about it, tan inverse looks something like this, where the limit is supposed to be at pi over 2. So that is going to be pi over 2. But hey, there you go, look. We basically compared what we need to solve for to something that's a lot easier. And we showed that in this case, since the upper function is convergent, then therefore, this one right here has to be convergent then. So the way that we can say it is the following then. Since the integral from 0 to infinity of 1 over 1 plus x squared dx is convergent, then the integral from 0 to infinity of 1 over 5 plus x squared dx is also convergent, okay, by the comparison theorem. So comparison theorem. All right, cool. All right, so now let's go ahead and take a look at this one last one over here. Use the same idea. In this case, this is something we definitely don't know how to take the antiderivative of. So that means that we're kind of stuck. You can use the techniques of integration, but again, that is probably not necessary. We want to try to make our lives a little bit easier if possible. So here, the question is, well, what do we compare e to the x plus square root of x to? Well, the comparison in this case is that this is always going to be greater than e to the x, which is very, very simple. Now, if you think about how that actually works out, this is what we're aiming for then, okay? This guy most likely will have to diverge in this case, because if we're comparing it to something that's greater, then therefore this is going to be diverge as well. We're basically using part 2 over here. If the under function is divergent, then that means the function above it is also going to be divergent. So that's basically going to be our aim. All right, so let's go ahead and write it. So we're going to say that the integral from 5 to infinity of e to the x plus square root of x dx is going to be, let's see, greater than the integral from 5 to infinity of e to the x dx. Okay, so now we're going to go ahead and solve for that one. So limit as a approaches towards infinity of e to the x dx, okay? And integral is going to be from 5 to a. So let's see, we're going to go ahead and change that. So now it's going to be limit as a approaches towards infinity, the antiderivative is just e to the x as we said, boundary from 5 to a. And that now gives me the limit as a approaches towards infinity of e to the a minus e to the 5th power. And that right there, as we just said, is going to be infinity minus e to the 5, so therefore is divergent. So similarly as above, we can say that since the integral from 5 to infinity of e to the x plus square root of x dx is going to be greater than actually here, let me kind of word this a little bit better, okay? Since e to the x is less than e to the x plus square root of x, then by the comparison test, okay, or not comparison test, but the comparison theorem, because the comparison test is something else, which is actually very similar, then the integral from 0 to from 5 to infinity of e to the x dx is going to be less than the integral from 5 to infinity of e to the x plus square root of x dx, okay? And the integral from 5 to infinity of e to the x dx diverges. Therefore, the integral from 5 to infinity of e to the x plus square root of x dx also diverges. Okay, I'm sure it could have been a little bit less wordy, but you'll get the idea over here. All right, well, there you go. Thank you so much for watching, and I'll see you next time. Goodbye.